Okay. All right. All right. So it's a great pleasure for me to introduce John Dever, which is at Three Rivers Credit Union. He works in Indianapolis as data scientist. So this talk is about use of pervasive use of data science in industry environment, in particular business intelligence, I would say, but also financial sector. Okay, so those of you which are interested in any aspect of this are going to benefit from the type of topics that John is going to discuss, but also make you understand what type of work or research as data analyst you would do in an environment like a financial firm. Okay, so there's a great connection that we're going to see in the things that you've learned with the things that you're going to see, but maybe you don't know exactly what expects you after graduation or something like that. And it's of great interest, and hopefully you're going to have several ideas of what to do next, or maybe you want to join the firm at a certain point, right? So without further ado, John begin his presentation. So thanks a lot.
Thank you, Scott. That sounds good. Is there a way to get rid of this screen?
Yes. Yeah. This one, yeah. Yeah. Yes, you can simply
Exit.
you can close probably. Should work.
Hello, everyone. My name is John Dever. I'm a data scientist at Three Rivers Federal Credit Union. I've been there about 10 months. Prior to working at Three Rivers, I worked in health economics outcomes research. There was more of a formal statistician where I did inference and point estimates. I have a degree, my undergraduate degree is in physics. I have a master's in statistics. I do most of my work in R, which I learned on my own. A little bit in Python. So the project I will be just talking about today is predicting loan default with time varying covariates and imbalanced classes. If you have any questions at any time, just let me know. You don't have to wait till the end. So why do we want to do a loan default prediction model? Early identification of loans at risk is a valuable tool not only to our institution, but also to the borrowers themselves. When we identify loans that are risk at default, we can reach out to the borrower and discuss alternate payment options, offer financial counseling, or restructure the loan terms, to help them, because the last thing we want to do is repossess their vehicle or whatever. We don't want them to default on the loan. And so these proactive measures, in addition to benefiting the lending institution, also benefits the borrower. If you can minimize the damage to their credit history and also avoid repossession. So the first thing starting out with a project like this is conducting research to see what's out there in the literature, see what other models have been published. And something to consider when going to this, when looking through the research, which is going to be non-systematic, is that these loan repayments are generally over multiple years, and financial conditions evolve over time with individuals. So we want to use the most up-to-date data where we can, and so we'll be using multiple observations for each loan, and using both fixed and time-varying covariates. So in the more formal statistical analysis that I had done in the past, something like this with multiple observations, we rather do in this type of a binary outcome. We do, I've seen done in the past or done myself, survival analysis with time varying covariates, also mixed effects models or generalized estimating equations. These are done just to there's going to be as multiple observations for an individual or for an account is going to have correlation within those observations. So these are measures to help take account of that. And so this is a different beast, so to speak, that we're tackling here. We're doing predictive modeling, And so what I found in the research that I conducted was survival analysis, a lot of logistic regression, and then some machine learning algorithms, random forest, avoid vector machines, extreme gradient boosting, and then I didn't really see anything neural networks for loan defaults, but I had seen it with customer churn models, and then that long short-term memory model is where they had multiple observations for repeat observations for the same data. And with those, with the literature, with the research, a lot of the analysis was done on the same data set. There was a peer-to-peer lending institution that had made their data available to the public. And so a lot of the reporting and the analysis was done on the same data set. And what commonly identified important predictors in the analyses were the FICO score, which is a score of the credit value of the person, their credit trustworthiness, the interest rate on the loan, the loan amount, debt to income, and then months on book, and that's just how long since loan origination. One of the papers I had come across, and I guess this was in general, this actually was a dissertation, default risk and marketplace lending, and found that random forest and gradient boosting trees had similar model performance compared to logic regression approaches. So what we ended up doing, the models, I'll go through them one by one, but we did logistic regression, two random forest models, and then extreme gradient boosting. So the first logistic model is a lasso model. It's a logistic regression where it's a linear regression on the log odds of the event, in this case default. The lasso parts is you introduce the penalty term. That's this lambda term over here. You want to use that. You introduce that to try and avoid overfitting. So you don't want it to overfit on your training set, and then it's more likely to perform poorly on test set data that it hasn't seen. The next model, random forest, the composite of multiple decision trees. So the decision tree is a series of decision nodes. Here, the top one is age, less than 50, greater than 50. And we want to split each branch with the ideal would be, to get as a pure branch as we can, and then, eventually a terminal node with all non-default observations in one node, all default observations in another node. And random tree is, like I said, a composite of many trees. The difference in the trees is created by randomness added for each tree, where the randomness is, excuse me, you sampling with replacement for your data set. So you can end up with the same observation multiple times in your data set, and then the number of features that you're going to use in the decision tree. Tuning parameters are the number of trees, and then the number of features. And as we'll see later on, this is a highly imbalanced data set. So what we did with this model, we did downsampling, and that's where we balance. We sample the in this the minority class is the default class, and so we sample the non-default class to be the same size as the default class. So we end up throwing away a lot of data, but in this, it's been proven or shown to be true that with a random forest, the more balanced data set you have, the better the results, the predictive probability. The next method is extreme gradient boosting. Again, this is a tree-based method. And here we're going to limit the depth of the tree. And these are termed weak learners, because we're only a few branches off the tree. And what we're going to do is we train the first tree, and then we get the predictions. We look at the errors, then we take those errors and we train them on the next tree. Then we combine the two trees, get another prediction, get the errors, use those errors, train them on the next tree, and so on, all the way down the line. The training parameters are the learning rate, and that's what how much each new tree is going to contribute to the prediction. The maximum tree depth, the minimum child weight, how many column, the proportion of column or features you're going to use in the analysis, the proportion of the data set, and then the number of iterations. And again, because it's highly imbalanced, we did downsampling. The final method is again random forest, but there's some modifications we made to the data set and to the algorithm itself. So this, the transformation of the data set, this was found in a paper titled Dynamic Estimation with Random Forest for Discrete Time Survival Data. And the data set, particular data set we're using is something they refer to as super person period. And this method we'll refer to as super person period random forest, or SRF for short. And what they do, the transformation with this data set is you take, you duplicate the data each time step all the way out to the end. So for you duplicate each time step for each subsequent time step. So in the middle here is an example of our data set here. Three observations for ID1, 2 observations for ID2. And so this is one time step apart. So the first row here for ID1 would be time start 1, time start 0, time stop 1. Second row would be time start 1, time stop 2. Third would be time start 2, time stop 3. And what we do for that, for each time start, we make a row for each subsequent time stop. So that first row, time start 0, time stop 1, we also now add a time start 0, time stop 2, time start 0, time stop 3. And we use the same covariate or the same feature values as the original time start 0. In this example, the x1 is a time varying covariate, x2 is a fixed covariate, and the default is whether they default or not in the observation. So we also repeat that with time start 1. We add this time start 1, time stop 3, and then the final one, 2 to 3, we don't need to do anything with because there's only one step. And then with ID2, they defaulted on the second time step. Their second row was the second time step. So any time stops that end with 2, we also want to mark those as default. So this is essentially a survival model of discrete time where we're measuring starting from 0 to time t. We're using the feature values at that time start to predict whether to default or not at that time stop. And this will greatly expand the size of the data set. And then, so that's transforming the data, and then we also tweak the algorithm. So the tuning parameters are the same number of trees, number of features, but we changed the split rule. The previous random forest split rule is a Gini index. Here we're using a Hellinger rule, and this is something because this is something you can use with imbalanced data, and with this super person random forest, we're not going to do any resampling. So the whole data set goes in, all observations. And something also to mention, whenever we do training, splitting into training, testing, validations, or with folds for cross-validation, we do selection by the account, and then all observations for that account go with the group they're assigned to. We don't split on observations, only by account. All right, so those are the models, and now there's data considerations we need to take into account when we're processing the data set. So the first is what loans are we going to use? There's many types of loans that Three Rivers offers. Mortgages, auto loans, there's credit cards, home equity. So there, and then within these loans, there's variation that it might be different enough that we don't want to include the same type of loan. So here we're going to use fixed, and the later slide will show specifically what loans we have, but no revolving credits. We're going to exclude line of credit. We're going to exclude business loans, and we're going to exclude mortgages. There's very few defaults in mortgages anyways, but it's a 30-year payment. It was different enough that we don't want to include it with an auto loan. So another thing to consider are the features themselves. Some we want to do relative measures and not absolute measures. One of those is FICO score, where we're going to be measuring the change in FICO score over time and not the absolute score. I'll say this now, so the time periods that we're going to measure are quarterly. And then the other relative measures are the balance and the elapsed time. We're going to use proportion for those. A $10,000 balance could be 95% of one loan, or it could be 10% of another loan. So we don't want to use absolute value there. As I mentioned earlier, also we're using time varied covariates. FICO score is one of those, and that's we get that quarterly. But it won't be available until the following quarter, the first month of the following quarter. So the original plan was to make this, have this predict out to the next quarter. But since we won't have FICO scores available until we're within that quarter, we made it predict out 2 quarters. And then finally, missing values. Well, I have a slide there. We'll discuss what we did with the missing values. Okay, so we decided what loans we want to use. We apply our inclusion criteria, and these were the results. Initially, we started out close to 190,000 non-default loans, 9,000 default loans. Make them they had to be consumer loans, and then the FICO data isn't available until Q2 2017, so we excluded anything before that time. That dropped us way down to 36,000 for the non-default, 1,800 for default. And they had a FICO score. Everyone didn't always have a FICO score. That knocked another 10,000 off and 600. And then finally, we're not going to use line of credit loans. And then this analysis started in Q4 of 2022. So Q3 2022 was the last time point. And we end up with 25,000, approximately 26,000 unique loans that didn't default, and 1,162 that did default. And to the right are the loan types. The majority are automobile. Other are term loans, non-collateralized. We have some motorcycle, boat, a couple land development type loans for land development. So the 25,000 and 1,100, those are just the accounts themselves. We take a new observation every quarter that we end up with 165,000, 640 non-default observations, and 1,100. The non-default, or excuse me, the default is always the last observation, so that doesn't change. 1,100. So you can see this is a highly imbalanced. Less than 1% of observations will be default. And with the data splitting, as I mentioned, we keep all the observations belonging to one account together. And we did a 75% training, 5% validation, 20% testing. Missing data. Some observations or accounts were missing what the monthly payment is. We just used the loan amount and interest rate to estimate that. FICO score, if it wasn't available, we assumed what it didn't change. It was same as the previous score. We also created 2 binary features identifying if the score for this quarter is known, and if the score for the prior quarter was known. Delinquency information, if it wasn't, we didn't have any, we just assumed it wasn't delinquent. Outstanding balance, if that wasn't available, we used the first prior available and the next available and assumed equal payments within that gap of that missing gap. And then other, that could be something like age at joining Three Rivers. If that wasn't available, we just assumed it was the overall mean. Okay, so we went through a process of examining all the possible features. We narrowed it down, then we split after we identified all the loans, we split it into training, testing, validation, and we did a further analysis with the training data, univariate analysis, where we looked at summary statistics for each feature based on default, non-default, and did a univariate logistic regression. And these are the categories of features that we ended up with. This isn't every feature, but it's just the general class or categorization of what the features were. There's two that aren't shown here, or excuse me, three. We also added binary features for what quarter was it, Q1, Q2, or Q3. So we had demographics, age, sex, how long they've been in Three Rivers, loan-specific characteristics, interest rate, what was the amount, what proportion is still outstanding, FICO score, change from last quarter, change from 2 quarters ago, change for origination, other products. So they could also have checking accounts or savings accounts or mortgage. Yeah. We offer a lot of products at Three Rivers, so they could have something else with this. So we looked at the history of what products they had with us. So it could be products that closed prior to origination, products that were open prior to origination that were still open, products that they opened after origination, products that they closed after origination, and then other charge-offs that they might have had since origination. Finally, delinquency, how many days delinquent, and then categories 30 to 60, 60 to 90, 90 plus, and then also a 30-day plus count, running count of delinquencies on past loans. The next few slides are just showing some of the differences observed in the univariate analysis for some of these features. The response is default on the x-axis there, no, yes. These are all box plots. So with the interest rate, we see that there's a higher interest rate for the default observations, which makes sense. They're going to have a higher interest rate because they're riskier. And so it's a good job capturing that risk, it appears, initially. They also had lower loan amounts. That could be either financial wellness, there's just they're riskier. There's going to be a lower limit that they're allowed to take out. And they ended up with lower payments too. So the higher interest rates didn't quite even out with the lower loan amount. So they also had lower payments. Next set here are, they had been with Three Rivers a shorter period of time. They were younger. They had delinquency more often. And they had a greater principal outstanding. And finally, FICO score over time. The observed change is more prominent over longer periods of time. We see with lag 1, which is what's the change from the previous quarter. We see with lag 2, there's a bigger shift in the decrease in FICO score with the defaults than with lag 1. And then from origination, there's even a bigger decrease. So it appears that with these default accounts that it's a buildup over time, where progressively gets worse for them. Makes it makes it harder to make the payments, and eventually they just stop making it. And with this is a correlation matrix of all the features that we're using. There's very little correlation between any of the features. The main one was the proportion of principal and the proportion of time remaining on the original term, which are inversely related. The earlier, after loan origination, the larger amount you're going to owe, and then vice versa with the closer you are to the end of the loan term, the smaller the smaller proportion of principal you're going to owe still. So the next few slides are getting into the results, but first we'll define the measurements. We'll go through the measurement definitions. True positive predicted default, an account defaulted. True negative predicted no default, an account did not default. False positive predicted default, an account did not default. False negative predicted no default, an account defaulted. Sensitivity, out of all the loans that defaulted, what proportion did we get right? Specificity, out of the ones that didn't default, what proportion did we get right? Positive predicted value of those that we predicted to default, what proportion did we get right? Negative predicted value of those we predicted not to default, what proportion we get right? And then finally, F-score, which is a harmonic mean of the sensitivity and the positive predictive value. And this was our measure to determine what the best fits were. So the training results here, I just pulled the best fitting model for each of the 4 algorithms. We did tenfold cross-validation with a predetermined grid where we just sampled across all possible permutations of that grid. Training parameters, we reviewed these, just a reminder what they were. These results, normally the actual results writes out to an Excel workbook and gives you the full list of every possible combination and then what the results were of those results. Again, the best algorithms, the best training models were based on the F-score. And we see here that there's wide variation in the F-score for the different algorithms. And that's largely due to the imbalanced data and the arbitrariness of the prediction cutoff. Generally, a value of 0.5 is used, where if it's 0.5 or above, you're going to predict that the event happened, otherwise it didn't. But that's not a good cutoff with imbalanced data. So for the the super person random forest and the lasso, we did a little pretest to try and come up with what's roughly a good value to use, and then with the XGB and the random forest, since we did the down sampling, we just kept it at 0.5. But as you see, we got a very wide variation in the F-score. So that's something, knowing that beforehand that we need to be more precise on what the cutoff, the best cutoff value to use. We set aside some data for the validation. So this here, we ran through all in 1% increments, different cutoff scores, and on the right here are what the best cutoff scores were for or the optimal cutoff scores for the best fitting models. And for the two where we didn't use downsampling, the lasso and the super person random forest, the optimal cutoff is closer to 0 for the random forest, and then the gradient boosting, it's closer to 1. Okay, for the test, we used the test data set to compare the 4 different model types, see which one performed the best. And the one that did was the super person random forest, F-score of 0.28. The random forest had the highest sensitivity, but the worst positive predictive value. The super person random forest had the sensitivity was very close to the random forest, but it had the best positive predictive value. And some of the important predictors across the models was the proportion of the loan balance outstanding, the beginning interest rate, the monthly payment amount. There's some unique to the models. One was at least for the last model was at least one mortgage open since loan origination, and this only occurred with a non-default, so this is 100%, and so that made the lasso coefficient very large for that model. For the superperson random forest, it not only predicted out 2 quarters like the other models, but it also predicted out up to whatever the limit was, in this case, 20 quarters. And so this first row here is the same results we just saw. We predicted out 2 quarters. We see when we go past 2 quarters that the predicted performance drops off rapidly over time. Or further out we go. So the sensitivity is slightly more than half of what it was when we go out at another quarter. Quarters 3 and 4 are roughly equivalent, but then when we go to 5 and 6, we get another drop down. So I think this does a good illustration of having the most recent available data for the loan. It's it's important. It's of a great value. The last thing we did was we tried combinations of the various models. We did combined all the tree-based models, and then combined all 4 models. For the 3 tree-based models, that's this first row here. The analysis we did, we split the test set in half to determine what are the ideal weights for each model, and then the other half to test on. So with this first model here, the 3 tree-based methods, the weights of each model are in parentheses, 32, 56, 12. And this was just a brute force search where we just one percentage increments for each weights, and we looked at all possibilities. And then the next was the lasso. We include lasso in it, and this actually in the weight search, it actually outperformed the 3 tree-based method. But when we got to the testing, you see that it overfit. It barely did better than the lasso by itself. And I believe the weights for this, it was like 60% lasso, and then everything else, XGB and 0 SRF, and then 2 or 4%, something like that, random forest. So it didn't, it overfit when we tried to combine the 4 models. So with all these predictions, it's multiple observations, and one account can have 5, 6 or more observations. So one thing I wanted to look at was how well does it do excuse me, on the account level. And so in this split test set, there was 129 default accounts, 2,589 non-default accounts. And when we look at false positives, 55 of the observations were for 25 accounts, which were later true positives. So these are the ones we just predicted a little too early. They would later go on to do default, but the timing was off in our model. And then there were 50 accounts that we predicted to default that never defaulted, which gives us a 2% error rate of the non-default accounts. And that's very important to us, is that the vast majority of the accounts are going to be non-default. And so we want to keep that error rate as small as possible. To the right is the full test data set now, where we use the 3 tree-based combined model, and we looked at what were the predicted probabilities. The red here is the false negatives, and we see there's some signal there, but not enough to classify them as defaulting. And then with the purple is the true positives, the green is the false positives. There's not the true positives are a little higher, but there's not much distinction. There's not very good separation between these two groups. We'll go through the next few slides, are just looking at some of the individual features based on those 4 classifications: false negative, false positive, true negative, true positive. So the graph on the left here, yeah, that's your left. So this is the y-axis is the proportion of principal outstanding. The x-axis is the proportion of time remaining on the original term. And there's a correlation matrix. There's a negative correlation. The slope's practically -1 here. And so this most of this data set here on this slope and to the lower left are the true negatives. That's the green. And we see within that a lot of the red circles. Those are the false negatives. And then up and to the right are our false positives and true positives. False positive being the green triangles, and then the true positives are the crosses, purple crosses. So we, again, the true positives and the false positive, we can't really distinguish between the two with these two metrics or features. To the right are the change in financial score from the previous quarter, or FICO score, and then the number of days delinquent. We see again a lot of overlap between the false positives, the green triangles, and the purple plus signs, the true positives. For age, we see false negative, true negatives are similar, and false positive, true positives are similar. How long they've been a member at Three Rivers? The false negatives are more like the true positives and false positives than they are like the true negatives. Same thing for interest rate. False negatives tend to have a higher interest rate. 30-day delinquency, as you'd expect, false negative, true negative are similar to true negative, false positive, similar to true positive. And so one question is, why are we predicting, are we not predicting these false negatives to default when they have these high interest rates and they're haven't been a member for that long? So the key takeaways, the superperson random forest outperformed all other individual algorithms, and it also allows predictions further out into time. However, the predictive performance dropped off sharply after when looking further than 2 quarters. Second key takeaway, although the vast majority of the data is discarded, downsampling was a useful technique in dealing with highly imbalanced data set. And finally, combining the weighted output of each of the tree-based algorithms increased predictive performance. However, a brute force search over the entire weighting space resulted in overfitting when the lasso model was also included. Next steps, improvements. How can we improve the model? Some ideas that I saw in the literature: external variables, the average S&P 500, federal funds rate, state unemployment percentage, maybe additional member-specific information such as transaction and balance data, and then also additional models, neural networks, long short-term memory, and maybe survival models. Any questions?
You have questions for comment? Yeah.
Thank you for the talk. So you mentioned that when you were doing the boosting, the way to balance classes was to downsample the majority class. So I understand that for random forest this is relevant because you are resampling from your training data again and again. But for boosting, isn't it adapting automatically to examples that haven't been predicted, say previous iteration, and resamples itself based on errors that it did?
Right, so it'd be learning, well, once it gets wrong, it's learning on, it's just giving more weight to those points,
so
it's missing on.
automatically upsampling those rare examples?
That's a possibility. I mean, that's a good question. I assumed that, since it's another tree-based method, that the similar principles apply for why you want to do random forest versus, with the gradient boosting. Same reasoning that, you don't want, you get that saturated amount because there's so much non-default data in there that you can't pick it up. But I mean, that's a very good point. That's certainly worth looking into.
Thank you. Also, could you please tell me what is Hellinger rule?
Yeah, it's a mathematical formula, just how to score the split. And it's a square root of something. Square root of something plus the square root of something.
And if I remember correctly, this was the rule to avoid this imbalance.
Right, yeah, so it's, yeah, the different type of scoring system where, well, with the Gini, index, it's, if you get like a 50-50 mix, that's not gonna score well, but with a Hellinger, yeah, that's something that would, show up well, and so that's something you wanna favor.
So why in some situations you use downsampling and
Just variation. So that paper itself, that's what they had used, the methods I was following that paper. I had used downsampling in the past, it worked well, so I stuck with it with the random forest, I'd done downsampling.
more?
Sure, yeah.
Okay, so in the list of loan in the list of loan types, I noticed that there were no mortgages.
Right.
Was it separately analyzed?
No, we didn't do an analysis on mortgage. Like I said earlier, there's very little default. Yeah, it's not worth it. All those differences of what's a mortgage versus the other loan products. It's all gonna be non-default data anyway, so we decided to keep it out.
My pre-last question is,
Okay.
in validation sample, you had 5%, in test sample, 20%.
Yes.
This looks to me unorthodox. I mean, in academic,
Okay.
benchmarks, we usually have a test validation sized.
Right, yeah, I was more concerned that, just that we have so few defaults that I want to, as much as possible in the test and just take my chances with the validation where it's just trying to determine what's the best cutoff to use.
In the box plots, I noticed there are many outliers. Could you tell approximately which are falling above the whiskers?
For which data? Any of them?
When you were talking about univariate analysis, yes, for example, here.
Right. I don't know off the top of my head. It's not many.
As in the box?
I mean, well, yeah, above I mean, the box is 75%. I don't know these additional outliers, but there's certainly, there were some. I wasn't, it's mostly the tree-based methods. I wasn't too concerned about it, but other models I would do a cap, some type of cap on what the maximum value can be for when doing predictive modeling, and come up with some rule for maybe four standard deviations over the mean. We set it to whatever that is, or anything top 95%, just anything in the 5% greater. We're just going to set the 95% value. Something, but I didn't do that in this instance.
To apologize. Sorry. As I said, I missed the beginning. So I understand this is really predictive models for
Yes.
accounts, right? So I have not sort of a non-technical question. I have more of a design question. When you looked at all the features that you include modeling, I didn't see, maybe I missed it, but I didn't see anything that would raise a flag for sneaking in discrimination like zip code, ethnicity, educational background, these kind of things. So was this a deliberate design decision? Keep it free of biases, or was it just, it so happened that you picked those and not the other ones?
Well, I mean, this loan default, I don't know how, I mean, yeah, there could be, so one of the possible ones was how far away they live from a branch. That's some location data that didn't have any predictive accuracy for whether it would default or not. But we have county that would probably be the most granular we could get with that, if we wanted to do location. And then again, it's gonna be, because we're mostly located, in Allen County, right? Yeah, so it'll be a few counties, then not in one of those few counties. But, discrimination, that didn't cross my mind at all in the analysis.
But he's right. From a regulatory standpoint, when we do get audited, we cannot do that. So if you would have included that, that would have been then. Right? Can't discriminate.
So you could just plug in by chance.
Yeah, by chance.
So there are some professional expectations I hear.
Yeah.
That you safeguard your modeling
Against yeah, in fact, he had gender, and he did look at gender. We've done a predictive model to even get to gender because we don't ask our membership. But so even that kind of. Right.
So thank you both. The other question I have, so I'm not knowledgeable in this field. Just assume that there is a correlation, say, between score. Because if you're older, then you have more time, like to build it up, right, and to make it better, and maybe to make like past mistakes, right, go away and all this. So if there are if we can assume that there are correlations, how do you account for them when you now build your predictive models?
Well, yeah, so yeah,
You have to whatever sort of hidden variables, right? Sort of. I mean, sorry, I will stop you.
yeah, no, I mean, yeah, that's a good point, but with the FICO, we actually, didn't do the score itself, we looked at the change. So that really wasn't much of a concern there, the change over time, between quarters. And there wasn't, we had that correlation matrix up there. There wasn't much correlation between any of the variables, but yeah, I would assume that there is a high correlation between age and FICO score, but I don't think we had to worry about that because we were looking at the change in FICO score.
That'd be an interesting study, but yeah, that doesn't mean.
Okay, the next time we have a topic for you.
Yeah, we equally see FICO scores.
Yeah, and generally with these loans, they have to have like an initial base level to get the loan.
Right. Yeah, things that hit me. I know the FICO scores on a quarterly basis. I think we had FICO score more often, like on a monthly, that would help you out a lot.
Yeah, and I think probably you just throw it right into the model with the change the time scale.
Just FICO, I mean, that stuff changes. And even in addition to FICO, well, FICO really only changes on a quarterly basis. But we have another score we get called Bandit. Maybe we should roll into the model. And that Bandit looks at some other factors like whether you pay your rent on time. Maybe they look at stuff you've done with appliance purchases, furniture purchases. So that one is more relative, and monthly Vantage changes. Who remember a credit at Three Rivers?
Oh, yes.
But yeah, most financial institutions will they'll offer you a free look at your credit, and normally what that is a Vantage score, not a FICO score, which is to us is really more.
Yeah, I don't see why we couldn't just, because the Vantage score didn't go back as far as the FICO score.
That's right.
So, but I think we could just substitute it in. They're roughly, I think they're equivalent enough that it probably would improve the model. Yes.
So at the end of your So if you training split 75-20, have more defaults in your training, would that cause any risk of your performances to have ability to where you might not have many defaults, or do you have enough where that's not really an issue?
So what's not really an issue? So yeah, that training size was 75%. And it was split on the default, right? So we get a balance of defaults within the three groups. And so you're asking, could you explain it one more time?
Basically, are there enough in the test set to feel that you can come with it being?
Yeah, I think so. So there were what 66, 160, 140 and 90, so 200, 32, is that right? Of the defaults in the training set. And there was 800 something in the training set. Sorry, so 230 in the test set, 800 something in the training set. Yeah, I think there's so many non-default that it's picking up. You know, it's getting 40% of the default. So even though it's just overwhelmed with that non-default, it's still able to. I think there was enough default in there that we see that the model is doing something. It is identifying at least some defaults. Ideally, it would be better to have more for the modeling, but not from a business perspective.
Yeah, no, we don't want.
So I have a common question about the imbalanced data, right? So from a perspective, Steve, right? Either your sample is representative of the population of interest or it's not. Now, if the sample is representative of the population of interest, but you don't want to change the sample. So if the sample is not representative of the population of interest, you want to know why it's not representative of the population of interest. Now, if the sample is representative of the population of interest and there is an imbalance, well, if you remove the imbalance, then you help the algorithm to perform well on the data that we train. But in practice, it's like, suppose that there is a rare disease which happens 1 over 1 million times. Well, then I adjust the data so that, it will be more balanced and maybe, logistic regression works better. But in practice, it's like you have an algorithm which works well in a case in a population which the disease is not rare anymore. But then the doctor is going to face the two population. So in practice, what I'm saying is that from another perspective, I can always adjust the data so that the algorithm performs the best. Even if I take into consideration, cross validation, all these type of things, right? I can always self-select the sample. And so what I'm wondering is, I would say, if the data that you have is representative of the population of interest, I would just adjust the algorithm, not the data. Because when you adjust the data, then you make the population not representative of the population of interest. So whatever algorithms works well there, then when you go into the population of interest, then it's going to perform better. So what I'm wondering, I don't know if this is the case, right? But if there, let's say that you have a case in which the data is not representative of the population of interest. So let's say if you have only male, samples, and the population is about 50-50. Well, then you have a problem there, because there you have a population which is not representative of the population of interest. Let's say you have 90% male, 10% female. Then you want to do something there, because that data is not representative. So if you have a data set which is representative of the population of interest, to have the algorithm by changing the sample so that it becomes not representative of the population of interest, you just have cons. So I would think about that, because it's like not having something you can deploy yet.
Okay.
So I'm always concerned about changing it. If the data is the sample is representative of population of interest, then it's a problem with the algorithm. If the sample is not representing the population of interest, then we have to figure it out that first.
Okay, yeah, that's a good point. I mean, that's something we could do too, is retest the with the random forest, and maybe use that Hellinger instead of the Gini. But I can't say that it's is the population of interest or not. I think it's probably they're different enough, the default population versus the non-default where they.
So I'm saying, let's say that in the true population, your sample is represented, namely that it has, like, let's say, more or less the same features.
Right.
Either sample both well, whatever you have, depending on all the features, all of them are represented. Right? You say that in the true population, 95% or 99% doesn't default, 1% default. Then you don't want to change that from a perspective, because then you're helping the algorithm to perform well, but you're modifying the data. And when you modify the data is not anymore representing the population interest. Then your model, you can always trick the model so that it's easier to run a model on some balanced classes.
Right.
But if the two classes are not balanced, then your model which works well on balanced classes, but the classes are not balanced in practice. So it's true that you can, work things around, but you don't want to change them. Let's say I have, you only have data for male population. All right, well, you have 90% of the male population, 10% female population. Okay, then you have to do something. Because whatever you want to do, you want to do something. Because the population is now 90% male and 10% female. Then you have to do something there on the data. But if the population is representative, I would caution you changing that, because you risk that you have good model on data which is not representing the population interest. And so in practice, you cannot say too much about what really is.
So you would suggest a different algorithm?
I would suggest that it might be tough work to do related algorithm.
Yeah.
Like, let's say like that. Like, if you have, let's say, the example before, a rare disease, 1/1 million, and then everybody else is healthy, right?
Right.
Well, if you have, you can just play with the balance, right? And then make sure that somehow, even if you're doing cross-validation and so on, like, if you rebalance the classes, you're surely going to improve your score. But then the doctor's going to see 1/1 million, which is sick.
Right.
And it's not like seeing like 50% sick and 50% not sick. So it's a risk, though, just changing that. So I don't know if you guys the qualities algorithm and then you change that. Yeah. Yeah.
Yeah, I actually was thinking about what you're saying from the very beginning, but when you are explaining this problem, I realized that sorry, I forgot your name.
John.
John.
Yeah.
That he works with the available data, right? And this is from customers which.
Yeah, but then you need downsample.
Huh?
Then you downsample.
Yeah, but we cannot assume that these clients of the
And
bank.
so you downsample, even worse. You change the data, you say you don't know what is the population of interest until you change the data. It's even worse.
But
it's even worse.
We cannot,
You say, I don't know what is the population of interest, so I just change the data.
no, but we cannot assume that this is the random sample of the population, right?
So then you say, I do even worse. I don't know if it is a random sample of the population, and then I still change the data.
Well,
It's just a worse. It's worse than this.
in a belief that it's better.
It's worse than this because you change the population without knowing if it's representative. And so you can change that. You don't do that. You first verify this. If you want to modify the data, you first have to know what the data is. But if you change the data, then it's not representative of the population. How do you change that? How do you decide how to change that? You don't sample them? Well, surely the people which default are not the same and not as many as people which don't default. If you want to decide to change the data, then you have to know how to change it. What is the reason for which the data is not representative? Otherwise, don't change that. So you just put your hand on something you don't know what it is. You don't do that.
Well, I guess the reason is that people who default are most likely not coming to ask for a loan.
So I say, but then let's tell me what is the representative the population of what is the true population? Because you don't know what is the population, and then you change the data to have.
Yeah.
It's even worse.
So maybe it
it's
makes
even worse.
sense.
You don't want to do that.
Yeah.
So either you know you don't. So the issue is always that. So either you know the population of interest or you don't know the population of interest. If you know the population of interest, if the sample is represented the population of interest, you don't change it. if the sample is not representing the population of interest, then you need to figure out why it's not representing the population of interest. Let's say that you have too many males and many females. That's simple. But if you have tons of issues, that becomes complicated. So every time you touch the data, you modify the data, you need to know how you do that. Because it's a risk that when you actually deploy the model, then of course it can still be belonging poorly, but at least you didn't put your hands on something that you don't know what it is. So I would caution that. Like I don't know if you guys deploy that.
No, it isn't deployed yet.
Yeah, but you know it's something that I would caution. Like if the data is representing the population of interest, I wouldn't change the data. The data is not representing the population of interest, then you have to figure out why it's not. Like it's a sampling procedure. It's the fact that people go, let's say, go to the doctor. People which are more sick go to the doctor. The type of situation. You don't know why. And then at that point, if the problem is that you have an imbalance between the people which can't deliver for whatever reason, then you can decide to adjust the imbalance. But before, it's kind of risky to modify the data because the risk to have a model which works on a population which is not population of interest. Because not only because it may not be representing itself, but because you changed it. So caution that.
Test set is also after downsampling, right?
No, the test set was just unchanged. Yeah, we split it, training, validation, testing, and just left the test set until we got done with the training and validation. And so that the training validation, excuse me, the training did cross validation tenfold, split it in there, and then
Where do you do downsampling? In training data?
yeah, in the training data, just in the training data. Yes.
Sorry, maybe I missed it. Second time is to limit the to avoid overfitting.
Just the only for the random forest, we just did the number of trees and the number of features. No.
It's that time because these different models give you basically completely different predictors.
Well, yeah, I mean, so that
That's tough, right?
yeah, they're different data sets too. I mean, maybe that's part of it.
Right.
But you know, some of the key ones, the outstanding loan balance, the beginning interest rate.
Other questions? Okay, they introduced also Vendetta, which is Director of Business Intelligence at I should have done at the beginning. First time it's at the beginning of the talk. Okay, good. Well, okay, let's thank John.
Thank you. Thank you, everyone.
Yeah, thanks, John.
Yeah.
Yeah, thank you. Yeah,
Glad to do it.
So the other thing I want to mention is about device. So would you recommend content on super prediction? I was gonna send this the link for that. So the content I think I have the link. I think I have to watch it. On predicting mostly are for the applications are nice, but there are also
Yeah, that'd be great.
Yes. Yeah, so I would mention that it's but that's sometimes it's how it is. Sometimes it's how it is. Like that's very nice. The opportunity is always very common time. So in practice, the concern for me is that you have help with the algorithms perform well by rebalancing the classes. But that tells you something about the algorithm. and that's less about innovation. And so it might be that usually when you have a balanced class and something like that, it might be soft, but maybe it's worth to struggle a little bit. So that's one concern. So a concern is that in practice the algorithm has been helped by the balanced classes. Now it's true that the sample is already now represented 47%. But in that case, you correct on that, you just increase the problem.
Yeah, it's something to think about. I saw with the lasso where we didn't do the downsampling, it was more conservative, right? Where we it's a higher proportion, more likely to predict that you're not going to default than the other model.
And then with the right, so it's tough. So this is one important thing to say. It gets tough, like it gets tough, and so because well, there are many comments. Let me just keep the one in balance classes, right? It is true that the agreements have suffered for classes which are unbalanced. Rebalancing the class and helping algorithm need to have an argument that, namely that the true population is balancing. If the true population is not balanced, then you don't want to that because you risk that the algorithm is good on a balanced population, which is not the true one. So that's what it's better about that.
Okay. Yeah, I'll look into it more. So that what I found, there's oversample, downsample, and then what's smoked, just make up some new observations. Those are the main effects I see.
Yeah. So it is possible that people make mistakes in the sense that they adjust the population so that the algorithm performs well.
Yeah.
But in practice, then the algorithm performs well on adjusted data.
Right.
So then there is trouble then.
Actually,
When you get actually and use it, and you
it's
get
not
it,
performing at all what you expected.
right? And that's what it's in every physical field because there is always a bit of shift in distribution. Okay. But of course, you don't want to mess the population up there. And of course, it might be another thing, but if it's
Thank you.
yeah.
I'll do more research on it. The super person, I didn't change that at all. It's the whole data set the whole time, and I did the best.
But also be always, in my opinion, be always like critical because also publish the test and I have some mistakes. Some mistakes are things that people tend to overlook. And one of the things we should overlook, okay, they don't lose money. But then firm,
Right, exactly.
you want to use the money, and then you're gonna lose money. And so, yeah. Good, awesome. So now, before we what are we thinking about? Yeah, I'll just, yeah. So, awesome, thanks. Yeah, thank you. Yeah, okay, yeah. Casting John the application on.
I will leave you to the expert.
That's our best man.
No.
Yeah, this is good. Yeah, so I was coming to meeting the stuff like so it's something that you might find mistakes often. So like the issue that so there can be some for which the class is forever found. But you don't know why they're in balance or you don't know why they're balanced. Who can answer that? I think it's good. Know why they're in balance. And they're let's say that. So data, the sample is represented the population. Because that's what you're gonna see. That's what we're gonna see. If not represented, then you figure out why it's not. Let's say that you just have only population, or you have only old population. So you don't figure it out before adjusting the data. Well, if you don't know how to figure it out, because it's complicated or whatever, there's not enough information. Of course, it's a problem for the model. Maybe you cannot do the model at all. But I would still caution against modifying it. If you know how to modify it, because there is a reason for which, let's say, you can sample from one lake and not the other, but you know how to go from one lake to the other. You can reconstruct the population of this lake from the population of this lake, or let's say, male population. You can reconstruct male population, female population from male population, then you're not adjusting. But the lines I feel that adjusting the classes is gonna help the algorithms perform better, but it's not gonna
change.
the population is gonna be what it is. And so when you apply an algorithm to a population which is different, then you're gonna have troubles in the performance. So that's what be careful now. Careful now. So start from is this some 40% of the population? If that's the case, don't change it. Don't do it. Don't sum. If it's not, then first thing is to figure out how to get the sum to be representative or what to do if we cannot do anything about the sum.
Yeah, I mean, it's the,
Yeah, bye, yeah, thanks for being here. Yeah, yeah, bye, yeah, bye. Yeah, good. All right, so let me close it.